Good day. The topic for today is congestion control. The performance of computer networks depends on a large extent on the kind of congestion that is there in the network. Actually this is once again a rather large topic. We will just touch upon some aspects of them. One thing we know by now, that in general in network and say data network or internet in particular, although multimedia and other content are coming in, but this is a largely it's a lot I mean it's first of all it's a packet based network, and it's a largely data network where because it's a packet based network, and it is announced sort of that we make only a best effort of delivering a packet, okay, nothing beyond that. Now, what exactly do we mean by best effort? Okay. So, the kind of strategies we can take for and most of this best effort has to do with how you handle the congestion. So, that is what we are going to talk about today. So, we know what is congestion. When too many packets are pumped into the system, congestions occur, leading into degradation of performance. Congestion tends to feed upon itself and backs up, and that we will see. And congestion shows lack of balance between various network components, and moreover it is a global issue, because a congestion may happen in some intermediate network because of packets being intermediate router, because of packets being pumped from various sources. So, in that sense it is a global issue. So, we have this intermediate node or this channel or whatever it is, and the demand is in the form of various sources pumping in packets at various rates, say lambda 1 to lambda n, and this is being serviced by the whatever the channel capacity or the router capacity. This is being serviced at the rate mu and going to various destinations. The problem is demand outstrips available capacity. Okay, so, this is the basically the congestion problem. An added dimension to this problem comes from the fact that although these lambda, mu, etc., these terms are coming from general queuing theory, and for simple queuing theory these are the arrival rates and service rates, etc. But although queues are there, but in general the statistics which the data networks follow are rather complicated. Okay. So, traditionally telecom networks would follow some Poisson distribution with inter-arrival time, exponential inter-arrival time, but data network, it has been seen that it follows something what is called as, it has a self similar traffic, okay, or heavy tail distribution, and that is a rather complex distribution, but one of its key feature is burstiness. That means data tends to come in bursts, and then there is a comparatively long quiescent period, and then again another burst comes. So, that is a problem which has to be handled, and when if several bursts arrive at a node at the same time, that particular node may get overwhelmed. So, if information about lambda 1, lambda, mu, etc. are known in a central location where control of lambda I and mu can be effected instantaneously with 0 time delays, then the congestion problem is solved. But unfortunately, we cannot do that, because we have incomplete information and we require a distributed solution. Okay. So, and with time varying time delays. So, this is what makes the problem a little difficult. Now, if you plot the throughput of a network vis-a-vis the load, I mean this kind of throughput versus load curves we have seen earlier when we have seen Aloha networks and CSM SCD, etc. But the network in general, this is what happens: as load increases, throughput also keeps on increasing, first at a same rate, and then it sort of starts going down, and it keeps going down because of the intermediate delays and other bottlenecks come into the picture, and then there is a area where the throughput does not increase any longer, and if you increase the load beyond that, there is a catastrophic fall in the throughput. So, this part is known as the knee, and this part is known as the cliff, and this catastrophic fall is called congestion collapse. So, knee is the point after which throughput increases very slowly and delay increases fast. We will see delay, we will just have another look at this graph. Cliff, point after which throughput starts to decrease very fast to 0. This is the congestion collapse and delay approaches infinity. Note, in an MM1Q, delay is equal to 1 by 1 minus utilization. So, that is, as I said that it does not always follow this kind of simple formulation. So, I mean, I was talking about the delay. If you note this, that if this was the previous curve, and as you plot the delay, first the delay is low, then the delay starts increasing. Then in this area where there are lots of packet losses and there is congestion collapse and throughput collapses, the delay also becomes very, very high, tends towards it becomes hyperbolic. All right. So, obviously, you have to I mean, take all precautions not to fall into this area at all. So, we talk about congestion control, whose goal is to stay left of cliff, that means do not go into the congestion collapse. Congestion avoidance, goal is to stay left of the knee, and right of the cliff of course is your congestion collapse region. So, goal of congestion control is to guarantee stable operation of packet networks, and a sub goal is to avoid congestion collapse. To keep networks working in an efficient manner, that is another one, you might put it that way. For example, high throughput, low loss, low delay, high utilization. Okay. Well, these are the goals, not always achievable, especially because we have a distributed system with insufficient information about the global picture, but anyway that is there. Now, to provide fair allocation of network bandwidth among competing flows in steady state. So, there has to be some kind of fairness if it is there, if all are equal. Sometimes all are not taken as equal, we will see that. Here let me just mention this point I was making earlier about the congestion. First of all, you must see that if there is a congestion at an intermediate node, what would happen is there will be a lot of packet loss over there. Now, these were so packets, various packets from various sources would be lost and the delay would become high. So, maybe many of them were sort of running a TCP protocol. So, who would again start retransmitting, and again, so what would happen is that as more and more packets are lost, more and more packets keep on getting pumped, and the delay sort of just like a traffic jam, it starts at one place, and then if the jam does not sort of resolve itself early, then it starts getting bigger and bigger, and it starts getting pushed towards the source. So, of course, so then your overall network throughput goes down even further. So, people start pushing in even more packets. So, such things may happen. So, these are the kinds of scenarios that we would like to avoid. Now, there are various policies at various levels that we can take for congestion control. So, let us look at the data link layer, open loop policies. So, one is retransmission policy. How would you retransmit? One example of this retransmission policy, let us say, is that suppose you have an Ethernet network with a CSMA CD going on, and then you have detected a collision. The question is, how do you, I mean, are you becoming persistent or non-persistent? You do a random backup, back-off, or exponential back-off, or what is your retransmission policy when you will try again. So, what is your retransmission policy? That is important. Similarly, other things like out of order policy, if packets are received out of order. Acknowledgement policy, do you acknowledgement or you do not acknowledge. For example, if you have acknowledgement also, acknowledgement for each packet also takes up network resources. Okay. So, if you acknowledge every packet, then there is going to be as many packets sent as many acknowledgements. Okay. So, that is a lot of acknowledgement for the network. That is a high overhead. So, maybe you take a policy of not acknowledging all the packets, could be some kind of flow control policy. So, we have seen some kind of flow control in TCP. So, we will look into more details and variations of it today. And then at the network layer you can have virtual circuit versus datagram. Okay. This is an important issue and we will look at it in more detail when we discuss QoS and multimedia communication. But the point is just at this point I can just say very simply, suppose there is a communication, very important communication going on between two hosts, and it is a very important or mission critical or whatever for them. Now in this case, so they will be exchanging a lot of packets. Let us say their packet is flowing in only one direction, so a lot of packets will be sent and we want some premium service for this. Now if you want to give a premium service to this particular pair of nodes, maybe they pay more or something like that. In that case you have somehow to distinguish that all the packets, you have to classify them that okay, they form some kind of a flow. So you have to have some kind of a virtual circuit between these 2 points in order to distinguish them. If all packets are on their own, then that is a different kind of situation where it may be more difficult to distinguish the flows between two specific nodes. Okay. So, virtual circuit versus datagram may be an important issue. Once again we will see more details of this when we look at RSVP and diff serve and things like that in the QoS, when we discuss QoS in a little bit more detail. Packet queuing and service policy, that means so that is again important. That means in the router a number of packets are coming in, so they are going to be serviced one by one. So they are going to be put in a queue maybe. Now the question is, do you put them in one queue, do you put them in several queues? If you have several queues, do you have the same priority for all the queues, or do you have different priorities for different queues, and so on. Packet discard policy. So this has to do with the buffer management of the router. If the buffer becomes full, which packet do you drop? Then routing algorithm, what kind of routing algorithm you use? Packet lifetime management, that means when do you say that okay, this packet's lifetime is over, you drop it or something, packet lifetime management. So these are the important these things at the network layer. Then so we were talking about open loop policies. Now you can have closed loop control, that means monitor the system to detect when and where congestion is occurring, pass the information to places where action can be taken, adjust system operation to correct the problem. So actually this is more sophisticated and actually in some sense it is better. The point is, say one router in between has becoming congested. Now if it can sort of identify the sources which are the chief sources of trouble, so to say, in the sense that it is pumping a lot of packets which cannot be handled here. If you could send a feedback back to the source so that he can control his behavior somewhat, maybe send less number of packets, then the situation can be handled. Or you can say adjust some system parameters like maybe window size in a TCP, or so these are examples of the kind of thing you can do with closed loop control. So if we say that there is some congestion, we have to have some way of measuring congestion, or you have to have some metrics for measuring congestion. Okay. So one is a percentage. I mean, these are some examples of things that you can look at. Percentage of all packets discarded due to lack of buffer space. All right. So that is maybe one measure. Average queue length in the buffer. Number of packets that time out and are retransmitted, average and standard deviation of packet delay. So these may be metrics with which you measure congestion. So if these metrics go beyond a certain level, then you might decide that okay, some congestion is taking place and we need to take some action in order to prevent the performance degradation in a sharp manner. Feedback mechanism can be various, as we have mentioned. Router on sensing congestion sends a control packet to the source, we have mentioned. a bit in every packet can be reserved to announce congestion. So, this bit, so if somebody gets this, so what it will do is that this bit will be set to announce congestion, or you can send, somebody can send explicit probe packets to ask about congestion. Implicit algorithms of course make only local observation, so that is always there. Then what you can try to do is that you can try to adjust system operations, adjust time constants to a near optimal value, decrease the load selectively if possible. The selectively because I mean maybe if one source somehow can be decreased, maybe all the others can be served very well, could be, because it goes below a threshold. Increase resources if possible, if that is possible. I mean that this of course is usually difficult. Now, let us look at one aspect of congestion control which is very important, which is done all the time by TCP congestion control. TCP, if you remember, uses the sliding window protocol. So, we have a window and a sender can send right up to the window size to the other side, and it will wait for acknowledgements, and he will keep on acknowledging, and as that he gets acknowledgement, the window will slide. Okay. So, that is one kind of that is the basic TCP. What we are going to see now are some variants of TCP, since TCP is a very important protocol, and application protocols like FTP, HTTP etc., they use TCP. So, a lot of traffic, lot of important traffic on the net is actually carried on TCP. So, that is why congestion control, the whatever we can do at the TCP level, that is important. And one of the chief tool for doing any congestion control by TCP is by adjusting the window size. So, there are various variants, and we are just going to look at some of those. TCP has a mechanism for congestion control. The mechanism is implemented at the sender. The sender has two parameters: congestion window, which is called this is a variable called CWND, and slow start threshold value, SS thresh. So, initial value is the advertised window size. So, when a TCP connection, there is an advertisement of window size, and this window size is taken as the initial SS thresh value. So, congestion control works in two modes. One is slow start, and in the slow start phase, the phase is slow start when the CWND value is less than SS thresh, and congestion avoidance, where that means when the CWND value is greater than equal to SS thresh. So, basically we are sort of trying to figure out whether we are on the left of the knee or on the right of the knee. So, if you are on the right of the knee, but left of the cliff, we are going to be careful. If you are on the left of the knee, then we can sort of, if and things are going fine, then we can sort of try to increase the load so as to increase the overall throughput. So, that is the basic idea. Now, initial values, this is a slow start, that means set CWND is equal to 1. So, naturally if the window size is small, say 1, so 1 unit will go and then acknowledgement will come back, and then only something else will go from this side. So, that is, so we are being very conservative, you are sending only a small bit of information. Now, note the unit is a segment size, 1 of what? 1 of a segment. So, TCP actually is based on bytes and increments by 1 MSS, maximum segment size. The receiver sends an acknowledgement ACK for each packet. So, this is the slow start. So, receiver must acknowledge every packet, so that the first packet that it receives, it can send the acknowledgement. Note, generally a TCP receiver sends an acknowledgement for every other segment. We will come to that later. So, each time an ACK is received by the sender, the congestion window is increased by 1 segment. So, what happens is that the sender has sent one packet, it has got the acknowledgement. So, actually the sender then decides that okay, things are fine, so maybe we can do better, that means increase the congestion window size CWND. So, we increase CWND by 1, so make CWND equal to 2. So, if an ACK acknowledges 2 segments, CWND still increased by only 1. That means, for every ACK there is increases by 1. So, if that acknowledgement increments only I mean acknowledges only 1 segment or 2 segments, CWND is increased by 1 only. Actually, the reason to acknowledge every other segment is to decrease the number of acknowledgements. Now, even if ACK acknowledges a segment that is smaller than MSS bytes long, CWND is still increased by 1. So, the point is that any time you get an ACK, you increase CWND by 1 when you are in the slow start phase. Now, but although it starts slowly, does it increment slowly? Not really. In fact, the increase of CWND is exponential. So, the congestion window grows very rapidly. CWND rises very rapidly. For every ACK, we increase CWND by 1 irrespective of the number of segments ACKed. The TCP slows down the increase of CWND when CWND is greater than SS thresh. So, actually, as you can see, suppose it sends 1 segment, receives 1 acknowledgement, CWND is increased from 1 to 2. Now, it can send 2 segments, segment 2 and segment 3. It will get back acknowledgements for segment 2, acknowledgement for segment 3. Now, CWND has become 4. So, it will it will send 4, 5, 6 etc. So, so 3 of them it has sent, and the acknowledgement for 4, 5, 6 will come. Now, CWND has become 7 and it will send more. So, you see 1, 2, 4, 7 is increasing quite fast, but because for each acknowledgement it is increased by 1, and when you are sending so many segments at a group, you are getting so many acknowledgements. So, CWND is increasing exponentially. Congestion avoidance phase is started if CWND has reached that SS thresh, then each time an ACK is received, increment CWND as follows. That means, CWND is equal to CWND plus 1 by floor of CWND, that is the minimum or rather the largest integer which is smaller than CWND. So, this is now increases only by a fraction, and while sending, of course, you can you will not send a fraction, whatever be the current CWND value, its floor, that many segments you can send. So, CWND is increased by 1 only if all CWND segments have been acknowledged. That means, if all the CWND all have been sent or acknowledged, then CWND increases only by 1. So, we are very cautious while moving to the right of the knee. So, assume that SS thresh is 8. So, what will happen is the round trip time is this is t equal to 2, 4, 6 etc. as time is going. So, CWND is first increasing exponentially, then it reaches the SS thresh, then it increases only slowly. Okay. That is the point. So, TCP assumes there is congestion if it detects a packet loss. Now, what happens if the response, what is the response to congestion? TCP assumes there is a congestion if it detects a packet loss. A TCP sender can detect lost packets via timeout of a retransmission timer or receipt of a duplicate ACK. Duplicate ACK has been received, which means that maybe some previous acknowledgement might have got dropped. So, that is why duplicate. So, anyway, something was got dropped. So, it senses that maybe there is some congestion. Now, there are different ways to sort of respond to this congestion. One is the TCP interprets a timeout as a binary congestion signal, which means that there is congestion as soon as there is a timeout. So, the sender performs, so CWND is now reset to 1. So, it becomes once again becomes very conservative, resets to 1. SS thresh is set to half the current size of the congestion window. So, whatever, I mean, before sending it to 1, whatever be the CWND value, you divide that by 2 and make that the new threshold, and slow start is entered. So, you enter slow start again. So, initially CWND equal to 1, SS thresh equal to advertised window size. New acknowledgement received if CWND is less than SS thresh, CWND is equal to CWND plus 1, else congestion avoidance, CWND is equal to 1 by CWND plus 1 by CWND with the ceiling of this. If there is a timeout, multiplicative decrease, which is SS thresh is equal to CWND by 2 and CWND becomes equal to 1. So, this is the typical plot of CWND for a TCP connection with TCP Tahoe. TCP Tahoe is one flavor of TCP that we have been discussing. We will discuss some other flavors also. So, CWND goes on increasing, decreasing, and increasing, then it keeps on increasing when things are good, etc. So, this may be a typical plot. So, this was TCP Tahoe, as I said, is one flavor. It uses slow start, that is 1 plus, and for every acknowledgement, congestion avoidance, that means make only see the after beyond SS thresh increase slowly, fast retransmit. I will tell you what fast retransmit is. TCP Reno also, there is another version of TCP, uses fast recovery, and then there are some versions of this like new Reno and SAC, etc. So, receiver sends now acknowledgements in TCP. Receiver sends acknowledgement to sender. Acknowledgement is used for flow control, error control, and congestion control. Error control, of course, if the acknowledgement is not received, then you send retransmit. So, that is the error control, and congestion control, as we are finding that ACK is used for controlling this. ACK number sent is the next sequence number expected. Delayed ACK. TCP receiver normally delays transmission of an ACK for about 200 milliseconds. When things are all right, so because it allows the packets to arrive before, so that it can send less number of acknowledgements this way, and ACKs are not delayed when packets are received out of sequence. So, when some packet is received out of sequence and something is a little out of the ordinary, maybe that came through two different paths. So, you do not delay the ACK, you send it immediately. Now, if fast retransmit, if you remember that TCP Reno uses fast retransmit, if 3 or more duplicate ACKs are received in a row, the TCP sender believes that a segment has been lost. So, then that means ACKs have come, that means some earlier packet has gone so many times maybe, but then that means most possibly the later packets or later segments may have it is quite likely that they have become they have got lost. So, what it does is that without waiting for the timeout to occur for this particular segment which has been sent, it assumes that maybe it is lost and send one again. So, then TCP performs a retransmission of what seems to be the missing segment without waiting for a timeout to happen, and then it enters slow start, that is, it brings down a multiplicative decrease of SS thresh and sets CWND to 1. So, this is fast retransmit, and fast recovery, it avoids slow start after a fast retransmit. That means, after a fast retransmit, intuition is duplicate ACKs indicates that data is still getting through, at least the duplicate ACKs got through. So, after 3 duplicate ACKs, set retransmit lost packet, okay, that is fine. SS thresh you decrease to half, but CWND is equal to CWND plus 3, and then you enter congestion avoidance. So, increment on CWND by 1 for each additional duplicate ACK. So, this is a fast recovery, but then after this you enter the congestion avoidance. That means, if you that means basically this is trying to tune the performance of TCP to get the maximum throughput without causing congestion. When ACK arrives that acknowledges new data, CWND is equal to SS thresh. So, enter, and after that enter congestion avoidance. So, this is fast recovery. So, TCP Reno for duplicate ACKs, it does fast retransmit and fast recovery. Fast recovery avoids slow start, and if there is a timeout, you retransmit and go to slow start. TCP Reno improves upon TCP Tahoe when a single packet is dropped in a round trip time, but if multiple packets are dropped, then of course TCP Reno is not cannot handle that. For that we have a TCP new Reno. When multiple packets are dropped, Reno has problems. So, partial ACK occurs when multiple packets are lost. A partial ACK acknowledges some but not all packets that are outstanding at the start of a fast recovery, takes sender out of fast recovery. So, sender has to wait until a timeout occurs. So, in new Reno, partial ACK does not take sender out of fast recovery. Partial ACK causes retransmission of the segment following the acknowledged segment. New Reno can deal with multiple lost segments without going to slow start. And then there is a selective acknowledgement. Here you can selectively acknowledge in the standard or original TCP when you give an acknowledgement. So, that is the next segment you are expecting. So, all others before that, all segments before that are acknowledged. So, here you can give selective acknowledgement, that maybe I have got this and I have not got that. So, issue Reno and new Reno retransmit at most one lost packet per round trip time. Selective acknowledgement, the receiver can acknowledge non-continuous blocks of data, that means SAC, selective acknowledgement of 0 to 1023, 1024 to 2047 and so on. Multiple blocks can be sent in a single segment, and in TCP SAC it enters fast recovery upon 3 duplicate ACKs. Sender keeps track of SACs and infers if segments are lost. Sender retransmits the next segment from the list of segments that are deemed to be lost, like fast retransmit. Anyway, so there are so people have tried various kind of what I should call heuristics to improve the performance of TCP. So, there are two competing demands here. One is that we want to maximize the throughput, and so if you can maximize the throughput, naturally the overall delay, congestion, everything will be small, and at the same time you will get your job done faster. But in order to push this maximum throughput, we should not get into a congestion, or I mean absolutely no is the congestion collapse. So, we try to guard against that. So, these are the various versions or various flavors of TCP for doing that. So, we will look at so we have looked at TCP. Now, we are going to look at some other topics once again associated with traffic engineering, this congestion control, and one is traffic engineering. That means, can you shape or can you sort of handle your traffic in a particular way so that congestion is less likely to occur. Now, there are various components of the quality, and this is all these builds to give a quality of service in a network, and at routers these may depend on packet classification and packet scheduling. At network entrance it may have to do with traffic conditioning. At routers or somewhere in the network you may do admission control. Between hosts and routers you may do signaling. So, these are the different components of QoS of a network. So, let us say you have a sender here and a receiver here, these are the intermediate routers. You can do traffic conditioning at the edge of the network. You can also do admission control here or somewhere else. So, these are the different components. Now, traffic conditioning mechanisms at the network boundary need to enforce that traffic from a flow does not exceed specification. Okay. So, we will look later at what kind of specifications we are talking about, what kinds of things that people may sort of agree on or negotiate about, that what are the parameters. But suppose from some source we had negotiated certain parameters and we find that that source is not sticking to that parameter. So, it is going way out of that. Then you have to do some policing. So, policing is drop traffic that violates the specification. The specification as was agreed between the service provider and the sender. Shaping, that means buffer traffic that violates specification. And marking, mark packets with a lower priority or as best effort if the traffic specification is violated. Let us look at traffic shaping first. Regulating the average rate of data transmission allows control algorithms to work better. Okay. So, so this is very I mean this is to be understood, as I mentioned earlier, that these computer networks, specifically data networks, our internet traffic etc., they are inherently very bursty in nature, all right, very bursty in nature. So, when it comes, data comes, it comes in one big bunch, and then for long periods there is maybe no traffic. Now, the trouble is, if you are if now the average, say the burst peak to the average ratio may be as much as 1:1000. So, that naturally brings up a very important issue, that are you going to design your buffer and other the network provisioning, would you do it for the peak or would you do it for the average, or maybe you do something for in between. Actually, doing it for the, I mean designing it for the peak, I mean if you had designed it for the peak, of course everything would work fine, but then that is becomes very expensive and not very practical in many cases. So, what is done is, so I mean of course you cannot do it for the average also, that may be too low, so maybe you are somewhere in between. So, one inherent problem is the burstiness of the traffic. Now, if you could somehow make the burstiness, I mean smooth it out a little bit more, then all your system would work much better. So, one way of doing that, of course, you have to buffer it somewhere, all right. So, this is what we are going to talk about. The shape of the traffic relates to some statistics about data transfer rates as well as its sensitivity to error, delay, jitter, etc. One famous algorithm known as the leaky bucket algorithm, it is a single server queue with a constant service rate. You know, if you have a bucket which is leaking, so drop, 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 drip, 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 it will I mean maybe the water will come out at a constant rate, and so the same thing, that if you have a queue, a single queue, and then you service it at a constant rate, that is the rate at which you are pumping data into the network. So, instead of the bursting, so if there is a burst, that will get absorbed in your buffer at the edge, so that towards the core of the network, in the core of the network the burst will not come. So, it will be a more sort of steady kind of flow. If a steady average kind of flow is also something beyond the capacity of the intermediate nodes, then of course the capacity of the intermediate nodes are to be increased anyway. So, that is the leaky bucket algorithm in short. So, the input buffer allows a bursty flow to be smoothed out to an even flow onto the network. It may be implemented in hardware or the OS operating system. So, it may be implemented either in hardware or software. Underutilized slots are written off. By this what we mean is that, so say so the packets are being serviced from this network at a particular rate, let us say once every t unit of time. Now, after another t unit of time, it will again try to service, and if it finds that the buffer is empty, then nothing, so it will not send anything. Again after t units of time, it will send exactly one, if something has arrived by that time, it will send one packet. So, that is the underutilized slots are written off. The algorithm can work on the volume of traffic rather than the number of packets also. Only problem, so this is fine, except that it is somewhat slow response time for inherently bursty traffic, which is quite often the norm. So, one way to handle a little bit of burstiness is by a token bucket. So, this again improves the throughput a little bit, and it can accommodate burstiness to a certain degree. Of course, we cannot allow all kinds of burstiness, because then that will get the burstiness will flow into the core of the network, where it will be more difficult to handle. So, this is a token bucket. It limits the input to specified burst size and average rate. So, traffic sent over any time t, capital T, is less than equal to r star t, that means the average rate multiplied by the t plus some burst size, also known as linear bounded arrival process. So, there is a bound on the arrival process. Excess traffic may be queued, marked, or simply dropped. So, for this what we do is that tokens are generated for the buffer at a fixed rate, which can be accumulated. So, this is the main point where this token bucket differs from the leaky bucket. In the leaky bucket, the underutilized slots were written off, but here if your time comes, you can gather you can sort of get a token, and you can collect or accumulate up to so many tokens, and then when a burst comes, then up to that many tokens you can send, alright. So, the longer time average is sort of held, because there is a limit to the number of tokens you can really accumulate. After that you cannot accumulate tokens anymore. At the same time, some burstiness, some a little bit of burstiness is allowed, because if your source is inherently bursty, so if you can allow some amount of burstiness, that will improve the throughput. So, for each token only one packet can be sent, but tokens can be accumulated up to a certain maximum. A variant is to allow k bytes per token. Essentially, it allows bursts up to a regulated maximum length, that is maximum number of tokens. A leaky bucket may follow a token bucket also, in order to make it absolutely smooth. So, this is just a diagram. There are bucket holds up to b tokens, and then there are so many tokens per second are accumulating there, and when a packet burst comes, so it waits for the token. If the tokens are not there, then it cannot send, but if the tokens are there, depending on how as many tokens are there, so many, those many tokens are removed and so many packets are sent into the network. Now, having talked about this, let us just mention what are the kinds of traffic parameters that may be negotiated or that are important, or that may be negotiated between the sender and the network service provider. One could be maximum packet size, how big is the packet. Token bucket rate, so what is the average rate. Token bucket size, that means how bursty it will be. Maximum transmission rate, so what is the maximum transmission rate. Loss sensitivity, is this flow very sensitive to losses, like if you are just doing some file transfer, it will be sensitive to losses. If you are doing some maybe sending some voice, it may not be that sensitive. Loss interval, at what intervals, if the loss can be very bursty or if the loss has to be averaged out or what. Burst loss sensitivity packets in terms of number of packets. Minimum delay noticed and maximum delay variation which are allowed. So, these are again very important for multimedia traffic. Quality of the guarantee, is it just best effort or better than best effort, that kind of thing. So, these are the flow specification of services. Now, just the quickly let us go through the other topics. One is in admission control. We will come to admission control and signaling in more detail when we discuss RSVP in the next lecture, when we discuss QoS and multimedia traffic. But just to mention it here, admission control is a function that decides if the network has enough resources. Admit new flow if enough resources are available, reject the flow otherwise. So, what you do is that you do some reservation of capacity through some protocol like RSVP, which we will discuss later, and if you find that you can reserve the capacity for this kind of flow, for this flow having this kind of parameters, then you admit it, otherwise do not admit it. Of course, this sort of assumes that we are having some kind of a virtual circuit. And there may be distributed admission control instead of a central admission control at the beginning. So, example is maybe end to end delay must be less than a delay bound D. So, calculate D1, D2 etc., and what you do is that from the source, if the capital D is of course specified by the source, and as it travels some reservation signal, then it sort of calculates the delay D, D1, D2, D3 etc., and if D is less than D1 plus D2 plus D3, then you reject it because you are unable to handle it. If it is greater, then you accept it. Some signaling protocol is used to reserve and release resources and to do admission control. As I mentioned, this RSVP etc., diffserv we will discuss in more detail in the next lecture. So, so a reservation may be reserve 1 Mbps. So, you reserve 1 Mbps, that request goes through. So, this is the congestion control in virtual circuit. One approach is admission control, not allow new VC till congestion goes away or route new ones around problem areas. Other is negotiate flow specification when new VCs are set up. This requires resources like buffer space, bandwidth, etc., reservation along the way. This of course, to do a lot of negotiation, etc., this takes again some overhead. One topic which we mentioned earlier, you remember the TCP/IP source quench, okay, or sometimes something called a choke packet. So, this may be used as a crude mechanism for handling congestion. Each router monitors each output line and calculates the utilization as a weighted sum of current and past utilization. Above a certain threshold, a choke packet with the destination is sent to the source and the original packet is tagged and sent along. On receiving a source choke packet, the source is supposed to reduce the traffic to the destination by some percentage. So, if that happens and if it works out, then that is very fine. I mean, this is the problem, you see, that a point where the problem or congestion is detected and the source, they are sort of distributed, I mean they are sort of remote to each other. So, whenever you this thing somehow you, I mean if you could send this feedback instantaneously, then you could do of course control the congestion much better, but that is not possible. You have to have a distributed algorithm where you work only with some local information and something that might come along with some particular packet. The source waits for some time before acting again on the next choke packet, because there may be multiple choke packets coming. That means for the same burst that it has sent, what happens is that it has created ripples of congestion along the way, and all the routers are sending a choke packet. So, it is going to, I mean, so multiple choke packets does not necessarily mean that these are independent. They may have come from the same source for because of the same source. So, it waits for some time before acting on the next choke packet. For high speed lines with a lot of hops, choke packets to the source is too slow. Okay. So, choke packets may operate hop by hop, thus distributing the pressure on buffers. So, that is again another point. These choke packets of course add to the network traffic, and it operates hop by hop, thus distributing the pressure on buffers. Now, we talk a little bit about scheduling. This is another way to try to handle congestion. Packet scheduling, this has to do with deciding when and what packet to send on output link, usually implemented at the output interface. So, suppose you have some switch or router, some network node now so which is sort of and a number of packets are coming out. So, what you might do, what you might want to do is to classify these packets. When we actually the point is, when we say the best effort, actually in this context actually this is the worst effort, alright. So, there are premium service and other kinds of service, etc., etc., and the rest are the best effort for with the rest. So, what you may have is that you may have various classifications for these flows. So, which may go into different queues, and then there is a scheduler which schedules that which queue to service next and how. So, that is the scheduler. So, this has a vital role to play on the kind of services and that each of the packets at the micro level and each of the flows in general at a higher level they get. Now, typically internet queuing, what we do is that we use FIFO plus drop tail. What is FIFO? FIFO is first in first out, of course. It is the simplest choice and used widely in the internet, and this first in first out implies a single class of traffic, which essentially means that we have a single queue. So, whoever comes in first, he is the one, and if everything is going fine, then he is the one who would be serviced first. Okay. So, it is a first in first out. So, that has to do with the scheduling, and there is a drop tail, that means arriving packets get dropped when queue is full regardless of which flow it belongs to or regardless of its importance. So, whoever, I mean, if the buffer is full, whoever comes next you just drop him, that is a drop tail. So, FIFO has to do with the scheduling discipline, and drop tail that means drop policy, which has to do with the buffer management, how you manage your buffer, that means how much of your buffer you keep empty or whether you allow the buffer to get full, whom do you drop when the buffer gets full, etc. These are the buffer management policy. So, we have a scheduling, actually they always sort of go hand in hand, that this scheduling policy and the buffer management policy, they always come in pair. FIFO issues. In a FIFO discipline, the service seen by a flow is convoluted with the arrivals of packets from all other flows. So, there is no isolation between flows and no policing, send more packets, get more service. So, just think about it, we have one single queue. So, whoever is pumping in more packets into it, he is more likely to be serviced. Okay. Of course, he will lose some packets also, but other people will also lose some packets, but it sort of favors, in some sense it favors somebody who is pumping data at a higher rate. So, he gets more service, alright. Maybe he requires more service, or maybe he is just it is just some kind of a rogue node. So, you cannot say, but anyway you do not differentiate between different flows at all. So, there is no isolation between the flows. Okay. If there is a flow which is very important, but sends less number of packets, he will get service much less compared to the one who is pumping a lot of packets. So, that is a issue with FIFO. And some drop tail issues, like say router is forced to have large queues to maintain high utilizations. So, that is a problem. So, larger buffers implies larger steady state queues or delays. So, the delay is more, that is one thing. Secondly, synchronization, n hosts react to same events because packets tend to be lost in burst. So, what would happen is that when the buffer gets full, all the packets, different packets coming from different sources would be dropped. So, all the sources would know that maybe their packets should time out or something. So, they would sort of act again in unison, and this acting in unison is always bad. Okay. Then you tend to take then you take another step which again is again wrong in some way. So, it makes the thing more bursty. And lockout, a side effect of burstiness and synchronization is that few flows can monopolize the queue space. So, these are drop tail issues. So, priority queuing, in priority queuing what we do is we have classes have different priorities and class and may depend on explicit marking or other header info, for example, IP source or destination, TCP port numbers, etc. Transmit a packet from the highest priority class with a non-empty queue. This have preemptive or non-preemptive version. So, this is the kind of scheduling policy which you might have. So, routers need to be able to classify arriving packets according to QoS requirements, this is packet classification, and transmit packets in order to meet the QoS. So, maybe you have a class A service which is very premium. So, there is a lots of dollars there, and class B service and class C service, and you might attach different priorities to these different queues and serve them that way. So, each router must implement some queuing discipline. Queuing allocates bandwidth and buffer space. So, bandwidth which packets to serve next, and buffer space which packet to drop next. Router maintains multiple, but is one this thing which is very widely used, weighted fair queuing. Router maintains multiple queues for each output line, one for each source. The queues are serviced in a round robin fashion. Instead of packets, the volumes can also be examined. Some sources can be given a greater weight than others. The point is, even if you do not give a greater weight, the point is the service which is premium, that may be much less number of people over there. So, automatically since the round robin is between the queues, automatically those having a premium class, since the population is low there, they get better service. You may use a few bits in header to indicate which queue or a packet goes into. So, that is also this thing. Lower delay and low likelihood of packet drop for maybe high end users. Okay. So, priority, round robin, classification, aggregation, these are the different mechanisms which we use. So, with this we come to a sort of the end of a short handling of this congestion control issue. It is not a very easy issue, because as you know that this is a global problem, but you have to take some local action so that it works fine. In the next lecture we will take up quality of service. Quality of service, as we have already mentioned today, that we have different kinds of requirements, different kinds of quality requirements for different sets of people. As I mentioned, that if you are sending a file, that means transferring a file, you do not want any bit to be lost, and it may be a very vital bit, so that it may be a binary for a source or something, that the whole thing may become junk if you lose one bit. So, it is very, but then if it goes in a jerky fashion, if it takes longer time, maybe you do not mind. So, that is one kind of quality you require. Another kind of quality you might require is that, say, when you are doing some kind of multimedia transmission like audio, video, etc., where I may sort of be insensitive to a few packets being lost or a few bits being lost here and there, but if the delay keeps on varying, if the delay is too large or keeps on varying too much, then I have a problem with the quality of reception. So, that is a different kind of quality. So, how to handle different kinds of qualities and how multimedia transmission etc. can take place in the network, that would be our next lecture. Thank you.
Good day. So, our topic for today is QoS and multimedia, that is quality of service and multimedia. So, we will just look at these one by one. Quality of service. Now, what is quality of service? QoS refers to traffic control mechanisms that seek to either differentiate performance based on application or network operator requirements, or provide predictable or guaranteed performance to applications, sessions or traffic aggregates. Well, it talks about a lot of things. The basic notion is this, that there are some applications which require one kind of quality of service. By the way, the quality of service may mean so many different things, but the most important of them are the delay, network delay, and the packet loss. All right, delay and various ways that delay.